Yeah, welcome back to today's class. Today we want to still continue on discrete math 2. I told you the last class we did Boolean algebra and binary state. And I said I was going to continue the remaining two, which is what? Truth table and switch theory. So without wasting much time, let's get right in. I told you in the last class that Boolean algebra and binary state, right? I told you these two are what? Discrete math operating at different layers. This one is at the logical layer. So logical universe, and this one is what? Physical layer, which is what? Physics. Right? That was what I explained to you in the last class. Now, this class we are looking at truth tables, which is what? This truth tables. Now, what question does this truth table answer? Truth table is simply saying for every possible combination of already decided state, what must the outcome be? That is the question that truth table is going to answer. Mentally, you can actually decide that, but machine cannot. So there must always be truth table embedded in every design, whether you explicitly decide or not. Once you do the combination, it must have a truth table. So it means the final output is actually a row, a complete row that is decided by the machine. So let's look at this. Now, if we are saying that binary state must exist before truth table can appear, it means in the case of design structure, it is what? Binary state to truth table to what? To Boolean algebra. But in the case of operational structure, but in the case of a design structure, it is from Boolean algebra to truth table to what? To binary state. It means truth table is actually the complete law of what? The logical universe. That is what it is. Now, what am I saying? I'm going to have something like this. I'm going to have something like this. I'm going to have something like this. So I will have this. This is our truth table, right? This is our truth table. So we said Boolean algebra is dealing with condition evaluation, and we are looking at operators and, or, and what? Not. These are the ones we are basically looking at. There are other ones. But looking at this, I'm simply saying that if I have this, so if I am having two symbols, truth table is dealing with what? Symbols, which is what? 0 and 1. These are the binary state. So if I have A and I have B here, and then A is 0, B is 0, what will be the output be? So this one will be what? Output. Right? What will be the output? If I have 0 and I have 1, what will the output be? If I have 1 and I have 0, what will be the output? And if I have 1 and I have 1, what will the output be? If I am using AND. Right? If I'm using AND, this is 0, this is 0. For AND, both conditions must be true for the output to be true. So we are looking at true as what? As 1, while false as what? 0. So if this is 0, that is false. This is 0, that is false. So AND will give you this place to be what? False. So if this is 0, which is false, and this is 1, which is true, AND is saying that both conditions must be true. So in this case now, one condition is false, so this will be 0. If this is true, this is false, AND is saying both conditions must be what? True. So must be true for the output to be true. So this is going to be what? False. So A is what? 1. B is what? 1. Then the output to be what? 1. This is for AND. So this is the truth table for AND. Now, if it is OR, which is this one, OR is saying either of these conditions can be true, and then the output to be true. So in the case of OR, this is 0, this is 0. What would this give me? This will give me 0 because both are 0. Now, this is 0, this is 1. OR is saying this place will be 1 because this is 1. Now, this is 1, this is 0. OR is saying this place will be what? 1. This is 1, this is 1. So OR is saying it will be 1. Then what is not? Not is simply a reverse of the input. So if the input is 0, then OR not, right, will give us 1. If the input is 1, not will give us 0. That is truth table, following the concept of following binary state. So it means that binary state has to be available before you can have truth table, right? Now, switch theory. The switch theory. So, which is the last one? What is the switch theory saying? Now, how do I take this truth table and use a physical device, switch, to achieve it? That is the concept of the switch theory. Okay? Now, to do that, we are simply going to do this. I'm going to physically use a switch device, a physical device for switching. So I am having, this is your switch in your house, right? Your switch on, off for the light, on, off button, right? The switch on, off. So how are you going to arrange this switch to get this truth table? Now for AND, it means the switches are going to be connected in series. So I will have another one here, like this, right? So I can have something like this. So let's say this is my bulb. Then I have this, and then I have this. So this is my bulb, right? And then this is my voltage. This is my voltage. So how am I going to achieve AND? So if this is the AND, right? AND is saying the two conditions must be true. So this is A, and then this is B, before this bulb can come on. It means if I close this one, so if both are 0, 0, 0, it means this switch is open, this switch is open. So this bulb will not come on. Now, this is 0, this is 1. So it means A is 0, A is open, B will close, right? What will happen? The bulb will still not come on. Now, for the sake of me not cleaning this. So if I change this place now to 1, and then this one to 0, so it means I'm going to close this switch, and then I'm going to open this switch. The bulb will still not come on. That is 0. So for the bulb to come on, I must close this switch, and I must close this switch. So that closing is 1, and then this closing is 1. Then the bulb will come on. You see, that is the switch theory. That's how I'm arranging the switch. Now, for the case of OR, so in the case of AND, switch were connected in series. But for the case of OR, switch will be connected in parallel. So I have this, then I have this, right? Then I have this, then I have, let me bring it up. So I have this, then I have this, then I have this, then I have this, right? So this is my bulb, then I have this terminal, right? So this is, I'm combining these together. So this is my voltage. So this is my 0, which is like the neutral, right? The neutral. Okay, this is the switch. So if I have here, so this is A, and then this is B. So what is it saying? It's saying for all, if either of them is 1, the output will be 1. So I'm saying if either of them is 1, the output will be 1. So I have my A here. If A is 0, so meaning the switch is open. B is 0, the switch is open. So even this one is here. It means this one will be off, right? This will be off. Now, if I close this A, or let's do this one first. This becomes 0. This is 1, right? So what will be the output? It means this one is open, then I close this. So what will be the output? This one is closed. So the circuit will be complete by flowing this way to like this, like this, to this one. So the output will be what? 1. Now, if I open this switch and I close this switch, so it means A is what? 1 and B is 0. What will the output be? So this time around, it will go from this part like this to this, and then this one. So the bulb will be on. So this place will still be what? 1. Now, if I close this one and I close this one, so both are 1, the output will still be what? 1. That is the concept of the switch theory. So you can see how I am using discrete mathematics. Then the on off, I told you, is just, this is the truth table for it. If this is 0, this is 1. If this is 1, this is 0. So you can see how discrete mathematics is being used to operate your motherboard at the physics layer, looking at Boolean algebra, looking at binary state, looking at truth table, and looking at the switch theory. So it is very important because in machine, we are dealing with 0 and 1. So that's why I had to take you through this first before we now get into other topics in mathematics. So this is what I want to show you in this class, understanding how your mathematical law is flowing down into physics and engineering, right? So till we see in the next class, bye-bye.